Hello, this is 5.1 variation functions. And we start off with a joke. What is reverse variation? And the answer is the relationship between the length of a driveway and the chance of backing in to a mailbox. Because you go in reverse. Okay, so the vocabulary today is, so the big ones you're going to need to know from this are direct variation, this one here, direct variation, and inverse variation. Joint variation, I consider it just to be another type of direct variation. And then combined variation is going to be a combination of both direct and inverse. And then this constant of variation here is something that we're going to be solving for a lot. So example 1 is going to be dealing with direct variation. That's the first type that we're dealing with. And it says y varies directly as x. So this word directly tips you off as to what kind of variation this is. And with direct variation, we're always going to use this form. Y equals k times x. K and x are multiplied in direct variation. And maybe you can think of it as the relationship between x and y is they're directly related with that multiplication there. And then it gives us these numbers. Y equals 14 when x equals 3.5, so let's plug those in. 14 equals k times 3.5, those are my y and x values. And then we got to solve for k. And k, as you see down here, is the constant of variation. So to solve for k, I'm just going to divide both sides by 3.5. And k is going to be equal to 4. 14 divided by 3.5 is 4. So we found our constant of variation, so we're going to plug it back into our original equation, and we'll get y equals 4x, because k is 4. So it wanted us to write it, and we did that. Y equals 4x. Now it wants us to graph that, so let's graph our direct variation function y equals 4x. Now, we can graph this. You guys know how to do that. This doesn't have any y-intercepts, so we know that it starts at the origin. And the slope is 4, so we go up 4, 1, 2, 3, 4, and over 1. And then we go down 4 and left 1. Oops, that's not very straight. Draw a line through there, and that's your graph y equals 4x. So go ahead and try this one on your own. Hopefully you did that. So we have direct variation again. Y varies directly as x, so we use this formula. And then it gives us y equals 6.5 when x equals 13. So we solve for k by dividing both sides by 13. And 6.5 divided by 13, 6.5 is half of 13, so that's going to be 1 over 2. So that's our k, our constant of variation. So then let's plug it back in to our original equation, and we get y equals 1/2 x. Hopefully you figured out that when I said do this one by yourself, you could just pause the video. So now we graph it. And you might find yourself, as we often are, tempted to skip the graphing part. when you're taking notes at home, but I would really encourage you to do this. The more you practice drawing out these graphs correctly, the better you are for it. So my graph is 1/2 x, so I go up 1 and over 2, down 1, left 2, draw a line through there, and that's my graph y equals 1/2 x. Okay, this one is also direct variation, but it's not a graphing one because it has to do with a circle. So let's read this. The circumference of a circle C varies directly, that tips us off, as the radius r. So our equation in this case, instead of y equals k times x, it's the same type of equation, but we're just going to use different letters because we're dealing with a circle. C equals k times r because we're dealing with circumference and radius. And then it gives us these two values to plug in for c and r. So we've got c equals 7 pi feet and r equals 3.5. So we solve for k, divide both sides by 3.5. Divide this by 3.5, and 7 divided by 3.5 is 2. So our k is going to be equal to 2 pi, because we got this pi up here. So then we take that and we plug it back into our original equation, and we get c equals 2 pi r. Well, you should recognize that one from calculus. The circumference of a circle is equal to 2 pi times its radius. So there you go. Okay, and then instead of graphing, it wants us to find the radius r when c equals 4.5 pi. So we can just take that value and plug it in for c. So we'll set c equal to 4.5 pi, and it wants us to solve for r. So it's going to be 2 pi r. So to solve for r, you simply divide both sides by 2 pi. That gets rid of those 2 pi. And then divide this by 2 pi. Oops. 2 pi. And r is equal to 4.5 pi over 2 pi. So I know my pi's are going to cancel out. And then we've got 4.5 divided by 2. And you can probably do this in your head. It's 2.25 equals r. And it's really important to remember to add your units, which is in feet. So it's 2.25 feet, which is a pretty big circle. It's like a hula hoop or something. Okay, try this one by yourself. Hopefully you paused the video and did that. This one says perimeter P of a regular, oh, this is not a circle, this is a dodecagon, which is a 12-sided shape, and it's also one of the funnest words to use in the English language. So perimeter of P varies directly as the side length S. So we've got the formula P equals K times S. It's direct variation. Okay, and then it tells us that P equals 18 inches when S equals 1.5, so let's plug those in. 18 equals K times 1.5, and then we solve for K. So divide both sides by 1.5, gets rid of those, divide 18 by 1.5, and K is going to be equal to 12. Sweet. So we found our constant of variation. That's our K. It's equal to 12. And then I'm going to take that and plug it back in to my K here. And I get the formula P is equal to 12S. So the perimeter is equal to 12 times the side length. which totally makes sense because we know that a dodecagon has 12 sides. It's pretty sneaky of these math book writers. So it says find S when P equals 75 inches. So we'll just take 75 and plug it into our P. So we get 75 equals 12 times S. Solve for S, which is the side length. Divide both sides by 12. And S is going to be equal to, I need my calculator for this one, 75 over 12 is 6.25. Again, units, so that's 6.25 inches per side. It's another very big shape. Okay, good job on that. That was direct variation. Now we're going to be talking about joint variation. So we did direct, now we're doing joint, and next is going to be inverse. So joint is very similar to direct, except you have 3 variables instead of 2. So with direct variation, we always used y equals k times x. That was our formula. But for joint variation, it's y equals k times x times z. There's a third player there. Okay? So, in this case, we're going to change the letters because we're dealing with the area A of a triangle varies jointly as the base B and the height h. So it's going to be A equals k times base times height. Okay, and then it gives us some values to plug in. So A is equal to 12 meters when B is equal to 6 and h, the height is equal to 4 meters. So I had my k in there, and I got to solve for k. So I'm going to divide both sides by 6 times 4, which is what? It's 24. So that gets rid of those. And divide that side by 24. 12 over 24 is what? It's 1/2. Cool. So now I take my k value and I can plug it back into this equation. And I come up with the equation area of a triangle is equal to 1/2 base times height. Which is also another aha moment because that is in fact the formula for the area of a triangle, as you learned in geometry probably. Okay, so now we got this last step. It wants us to find the base when A is equal to 36 meters squared and your height is equal to 8 meters. So 36 is equal to 1/2 base times 8. So let's go ahead and solve for our base. We can begin by dividing both sides by 8. Divide by 8. And 8 goes into 36. If I'm not mistaken, well, I better use my calculator. 36 divided by 8 equals, oh, it's 4.5. No wonder that wasn't coming to mind right off the bat. So 4.5 equals 1/2 times base. And then to get rid of that 1/2, I divide both sides by the reciprocal, which is 2. So that gets rid of the 2 on top, 2 on bottom. Multiply this by 2. And base is equal to 9 meters. Don't forget about those units. What's up with all these really giant shapes? All right, try this one by yourself. This is another joint variation. Okay, so we got the lateral surface L of a cone varies jointly. So we've got lateral surface equals K times the base radius, so R, and the slant length, little l. Okay, and then we plug in chug. So L is equal to 63 pi equals K times, what's our R value? 3.5. And our little l, our slant length, is 18. Now to find K, I'm going to divide both sides by 3.5 times 18. So I'll go ahead and multiply those together to simplify it. We got 3.5 times 18 equals 63. Oh, that's nice. So that gets rid of those. And then we divide 63 pi by 63, and we find out that k equals pi. So we plug our k value in to our original equation, our k, and we come up with the equation L, which is lateral surface area. So I wonder what that means. It's probably like the surface area of the cone. That's like everything except for the base. It's my guess. Anyway, there's the equation. And it wants you to find the radius of the base to the nearest tenth when L is equal to 8 pi and little l is equal to 5. So then we're going to plug in pi times r, and we have to solve for r. So what do? We can divide this side by 5 to get rid of that 5. Divide this by 5. And then we can divide both sides by pi to get rid of that pi. And that gets rid of that pi. And we have r is equal to 8/5. And it wants it to the nearest tenth, so let's put that in decimal form. So 8 divided by 5 is 1.6 units, 1.6 meters. I didn't draw that box very well, so I'll circle it. Okay, good job. That was joint variation. So we've done direct, we've done joint, and now we're doing something else. We're doing inverse. Inverse variation. So a little bit of review. For direct variation, the formula was y equals k times x. For joint variation, the formula was y equals k times x times z. For inverse, it's y equals k over x. So x and y are inversely related, not jointly related like they are in, not directly related like direct and joint. They're inversely related. So this is your magic formula for these problems, okay? So y varies inversely as x, and y equals 3 when x equals 8. So let's plug and chug. We've got 3 equals k over 8. And we solve for k. So how do we do that? We've got 8 on the bottom in the denominator here. So let's multiply both sides by 8. That'll get rid of that. Multiply this by 8. And k is going to be equal to 24. So let's take that k value and plug it back into our original equation. And we come up with the equation y equals 24 over x. So we just wrote it down. That's what it wanted us to do. But it also wants us to graph this. So look at this. Look at this equation right here. And think about graphing that. What would that look like? Have we ever seen anything in this class that looks like that? We haven't, actually. So let's graph this. This is exciting. I'm introducing you to a brand new function for the first time. So let's graph this. Actually, let's graph the parent function first. So the parent function of 24 over x would be 1 over x. Okay, that's the parent function. And you can think about this 24 right here as a value being multiplied to the parent function 1 over x. So we had 1 over x and we vertically stretched it by 24. Okay. So I'm going to make a table of values. We've got x over here, and we've got y equals 1 over x here. And I'll start at -3, and I'll plug in, I'll plug in some x values. 1, 2, and 3. So for my y, we've got 1 over -3, which is -1/3. 1 over -2, which is -1/2. 1 over -1, which is -1. And then 1 over 0 right here. What is 1 over 0 actually? What is that? It's undefined. It's undefined. It doesn't exist. We can divide 0 by numbers, but we can't divide numbers by 0. It doesn't exist. So that's going to be interesting. And then down here, 1 over 1 is just 1, 1 over 2 is 1/2, and 1 over 3 is 1/3. So let's draw a graph. Okay. So this is exciting. It's the first time we are introducing you to this graph. So at x equals -3, we're down here at -1/3. X equals -2, we're at -1/2. X equals -1, we're at -1. And then at 0, we're undefined. Okay, there's no value there, so I'm not going to put anything there. And then over here at 1, we're up at 1. At 2, we're up at 1/2, and at 3, we're up at 1/3. So look at those dots. How are we going to draw a line through there? Are we going to go like this and then jump up like that? Well, at 0 here, it's undefined, so I don't actually have a line there. So that's not how it's going to be. Let's think about this. What if I wanted to put a value at x equals 1/2? Well, if I plug that into my parent function, it would be 1 over 1/2, which would be 2. So I'd have a dot up here. So actually what's going to happen is my graph looks like this. It comes through these dots, and then it plunges down to the depths coming from the left. And then coming from the right, goes through these dots, and it shoots up skyward to the heavens, as it were. And that's our graph. Look at that, people. Look at that. This is 1 over x. That's what it looks like. So let's do the mathematician thing that we do and mark our asymptotes. We already discussed that it's not going to be able to cross the y-axis. Okay, it's undefined right there. But it's also never going to cross the x-axis. It's going to keep getting closer as it goes to the right, or closer as it goes to the left, but it's never going to touch. So let's do this on our graphing calculator and see what our original 24 over x is going to look like. So I'm going to graph 1 over x, the parent function, and then I'll graph 24 over x to see what that looks like. Oh, come on now. What are we doing? Quit. Y equals... Well, what I'm going to do is actually close out of this because I think it's been preset some way. But if you have one at your house, you can do this without me. Okay, hopefully this will work this time. So we've got 1 over x and 24 over x. Now look at that. This one, this smaller one in the middle is our parent function 1 over x, and then this one out to the outside here is 24 over x. So it's a vertical stretch by 24. Super cool. Okay, let's keep moving. Try this one by yourself. I want you to write it and graph it. Okay, I'm going to do this one fast. We have this equation, y equals k over x, and it tells us that y equals 4 when x equals 10. So when I solve for k, I multiply 10 to both sides, and we get k equals 40. So we have the function y equals 40 over x. Awesome. So, oh, this was a warm-up, so we technically didn't need to do that one, so I won't graph that one for you. Sorry about that. Okay, community service application. The time t that it takes for a group of volunteers to construct a house varies inversely, so that tips us off as to what this is going to be. Varies inversely as the number of volunteers v. Okay, so we've got time t equals k over v volunteers. If 20 volunteers can build a house in 62.5 working hours, okay, so that's our t, 62.5 working hours equals k over how many volunteers? 20. So let's solve for our constant of variation. So we're going to multiply both sides by 20. Multiplying 62.5 by 20. 62.5 times 20 is 1250. K is equal to 1,250. So we get the equation y is equal to, or not y, we're doing t and v. T is equal to 1,250 over v, over volunteers. Now it wants to know how many volunteers would be needed to build a house in 50 working hours. So we're solving for v. It gives us t. So we're going to, rewrite this as 50 equals 1250 over v. We got to solve for v. Now, our variable is in the denominator, right? It's on the bottom. And we can't solve for it there. We gotta rescue it, get it out of the dungeon. Whenever you see your variable in the denominator, you got to get it out of there. So how do we do that? Well, we can multiply both sides by v, and that'll just get rid of this one and this one. And then we have 50v equals 1250. Divide both sides by 50. See if you can beat me to it with your fastest calculator in the West. Bet you didn't beat me there. V equals 25. Is that right? 1250 divided by 50 working hours. The answer is 25. Yep. Okay, we got that. So 25 volunteers can build a house in 50 hours. Seems pretty fast to me. That's like a full work week plus a little bit of overtime. Okay. So now we've got some direct variation and inverse variation equations for k. So let's read these. In direct variation, the blank, fill in the blank, of the two quantities is constant. So it wants to know what the quantities are when the quantities are the constant. So the constant is k. So when is k equal to the two quantities? Okay, so we're in direct variation. We know that in direct variation we have this formula, y equals k times x, right? We used that one earlier. But it wants to know when the constant is these two quantities. So let's basically solve for k and divide both sides by x, divide by x. So k is equal to y over x. When the quantities are being divided. So when they're divided, what do we call that? Well, we call that the quotient. The quotient of the two quantities, y and x. That's our constant. In inverse variation, we have the formula y equals k over x. And if we solve for k, we multiply both sides by x to get rid of those. And we get k equals y times x. So in this case, in inverse variation, for our constant, the two quantities are being multiplied. So that would be the product. Okay. So you're going to need to know this in the next slide. So it would be a good idea to memorize this, or at least how to get there. So if you have these original equations memorized and you know how to get from there to here, at least know how to do that, okay? Because when you're dealing with data sets like this, it's going to be really, really useful. So we've got data sets, and it wants us to determine whether each data set represents a direct variation or an inverse variation, or neither. So we've got x values and we've got y values, and it wants to know how they relate. Do they relate inversely or do they relate directly? So let's write down the different ways they can relate. If they were to relate inversely, then we would be using the formula k is equal to y times x. Right? We just figured that out on the last slide. If they were to relate directly, and I probably should have written this one first because directly usually comes first, but anyway, we would be using the formula k equals y over x. Okay, we divide them. And you say, well, Mr. Fink, I thought that the equation for direct variation was y equals k times x. Well, it is. But this one we're starting with k. Okay, and we are seeing how the y values and the x values are related. Are they being divided or are they being multiplied? So let's take this data set and see if we can figure out how our y values and our x values are related to each other. And I hope this makes sense the way that I'm explaining it. So let's try to divide them. So if we go with this one, if we go with direct, we can try y divided by x. So in this case it would be 9 divided by 3 equals 3. This one would be 24 divided by 8 equals 3. This one would be 30 divided by 10 also equals 3. So they all divide to 3. So that means we used the quotient, right? We divided them. So that means that they are related directly. Direct. It represents direct variation. That's a better way of saying it. It represents direct variation. Okay. So now this one, we want to see what kind of variation we have with our y and x values. So let's just look at this and see if we divided them. If we divided 8 by 4.5, we'd get something like 1.8 or something. And then if we divided 3 by 12, we get a very small number, like 0.2 probably. So I don't want to divide these because I know that that's not going to work. So if I multiplied them, let's try that. Let's take the product. So here we've got 8 times 4.5. I could probably do this in my head, but it's pretty late, so that's my excuse. That's 36. We've got 3 times 12. That's 36. And we've got 2 times 18. And that is also 36. Sweet. So we got 36, 36, 36, and we did that by taking the product of our x and y. So x times y equals k, and we know that that is an inverse variation. So this represents inverse variation. Okay. Try this next one on your own. And hopefully you did that. I'm just going to tell you what they are. I'm not going to do them. If you took the product on this one, if you multiplied them, you would get 45, 45, and 45. So this is, we took the product, so this is going to be inversely related. Inverse variation, I should say. And then for this one over here, 6b, if you were to multiply them, it wouldn't have worked. They wouldn't have equaled the same thing. So if you took the quotient, if you divided them, i.e. I don't have enough room, ENT, it would have worked. And you would have gotten 0.2, 0.2, 0.2, and you did that by taking the quotient, so you know that this represents direct variation. Okay. So in review, if it wants you to figure out if it's direct variation or inverse variation, try to multiply your x and y values or try to divide your x and y values, and whichever one gets you the same either quotient or product indicates if it's direct or inverse variation. Okay, this is our last slide. And we did direct variation, we did joint variation, we did inverse variation, and now we're doing combined variation. It's a combination of both direct and inverse. So let's read this. We've got the volume V of a gas varies inversely, that's our clue, as the pressure P. Okay, we'll stop there for a second. See if you can write out the formula before I do. So pause this video or something. So we've got V equals K over P because it's inverse, okay? So let's keep reading. And directly as the temperature T. So normally, if it was directly related, it would be V equals K times T. And this case is no exception. We've got V equals K over P, but we're just gonna multiply this K by a T. So this is an example of combined variation. Okay. And it tells us, so I'm going to keep reading. It tells us that a certain gas has a volume of 10 liters. Okay, so I'm gonna plug and chug here. We've got 10 for our volume equals K, that's our constant, and a temperature of 300, so K times 300, and it has a pressure of 1.5 atmospheres, so it's all over 1.5. And it wants us to solve for K, our variation constant. So see if you can do this one by yourself. Pause the video and try that out. Hopefully you did that. So I'm going to get rid of this 1.5 first. So I'm going to multiply both sides by 1.5, and that gets rid of that and that. Multiply this by 1.5, and we have 15 equals K times 300. So to isolate K, I'm going to divide both sides by 300. And we have K equals 15 over 300, 0.05. K is equal to 0.05. Awesome. So now I just got to take my K value and plug it back into my original equation. and I get volume equals 0.05 times the temperature over the pressure. All right. If the gas is compressed to a volume of 7.5 liters and is heated to a temperature of 350 degrees Kelvin, what will the new pressure be? Okay, so let's just plug and chug. We've got a volume of 7.5, and then we've got our K constant 0.05, and then the temperature is 350 degrees Kelvin over P. We have to solve for P, our pressure. The variable is in the denominator again, so we have to get it out of there in order to solve for it. We can't solve for it when it's in the denominator. So let's multiply both sides by P, and that gets rid of this one. Multiply this by P, and we get 7.5 P equals 0.05 times 350. So I'll plug that in here to simplify things, and I get the value of 17.5. Then to solve for P, I'm just going to divide both sides by 7.5, and I get 2.3 continuous. So my pressure, I'll do it in a different color. My pressure is equal to 2 1/3 atmospheres. And that is 5.1 for you. Very good. We've done direct variation, we've done joint variation, we did inverse variation, we learned a new graph, 1 over x. We figured out if data sets were representations of direct variation or inverse variation, and we just did combined variation. So, very good job.